Hello YouTube fam, welcome back to our channel. In this channel, we will be discussing various topics in the exciting world of AI, machine learning, and computer vision. Our content is crafted by our awesome human team, but here's the magic. It's finely tuned and optimized by our AI wizards, bringing you top-notch information. And guess what? The presentation is delivered to you by our AI hosts and voiced by our incredible AI avatars. Let's get started. Hey everyone, welcome back to another exciting video on our channel. Today's topic is a game changer. We're delving into the world of Retrieval-Augmented Generation to supercharge our language models. We're unlocking the secrets to enhance our LLM outputs. First on the menu is mastering the art of basic prompting. We then discuss a sample architecture for Retrieval-Augmented Generation. Finally, the fun part. We'll dissect a sample code to bring this technique to life. Today, let's unravel the magic behind the basic prompting technique, a pivotal strategy in the world of language models. It all begins with a simple query we want our LLM to bring to life and generate completion. Whether it's an open source or third-party LLM, we're transforming that raw query into a tailored prompt, a linguistic key that ensures the LLM comprehends our intent. Once armed with this linguistic arsenal, we hand it over to the LLM, which, like a creative maestro, generates the completion we've envisioned. Now let's delve into a drawback of the basic prompting technique. While LLMs are trained on vast data sets, they may lack specific information about proprietary company data. This gap sometimes leads them to make assumptions, resulting in what we call hallucination, the generation of information not grounded in reality. But fear not, there's a solution on the horizon. The Retrieval-Augmented Generation (RAG) technique steps in to address this limitation. By providing LLMs with access to proprietary data, RAG aims to enhance accuracy and mitigate the risks of hallucination. Stay tuned as we unravel the magic behind RAG in our next segment. All right, let's break down Retrieval-Augmented Generation (RAG) using the power of embeddings and vector databases. Earlier, we discussed that we need to provide LLM with proprietary data. Let's say we have that information in documents or databases. Let's say we have an internal knowledge base. We don't want to give all this information in its entirety to LLM, and it's technically not possible. We want to retrieve only the relevant information from the knowledge base and provide it to the LLM. Embeddings serve as compact representations of text, capturing its essence in a mathematical form. Vector database is a sophisticated system which can store the embeddings, and it enables efficient searching and retrieval based on similarity. Let us see it in detail. As a first step, we would perform embedding on the data in our knowledge base and store it in a vector database. When we see a user query, we would do embedding on the query and search the vector store for similar relevant content. This is the retrieval part of RAG, and the output of this step is similar relevant content from knowledge base. Now we combine the original user query and the relevant content from knowledge base to form an augmented prompt. This is the augmented part of RAG. We hand it over to the LLM, which, like a creative and more knowledgeable maestro, generates the completion we've envisioned. Next up, we will look at a code example to understand RAG further. We will use openai model as our LLM. We will use Facebook AI Similarity Search library as our vector store. To integrate all this, we will use the Langchain framework. Langchain is a framework which makes working with LLM easier. It provides different APIs to integrate with documents, vector stores, embedding models. We will start off with a basic prompt, and we will see how the LLM hallucinates. We will then incorporate the RAG technique we discussed earlier, and we will then amaze ourselves by seeing the LLM produce better outputs. To demonstrate hallucination in LLM, we will start off with a basic prompt. We will use a query based on the TV series Sacred Games. Sacred Games is an Indian thriller streaming television series based on a novel. It is a Netflix original series. The background premise I would like to tell now is that there is a scene where the name Ramakant Jadhav is mentioned in the show, but apart from that, there is no other reference to that name. So, there is no Ramakant Jadhav in Sacred Games. It is a fake person mentioned in the show. There is no actor who plays Ramakant Jadhav in the show. We will ask the LLM, who is Ramakant Jadhav in Sacred Games, and which actor portrays Ramakant Jadhav in Sacred Games. As we can see from the output, the LLM answers us saying, Ramakant Jadhav is a police constable and a close associate of Inspector Sartaj Singh. He is portrayed by the actor Rajshri Deshpande. Ramakant Jadhav plays a significant role in assisting Sartaj in his investigation throughout the series, but this is definitely not correct. Also, the name Ramakant usually refers to a male. The LLM answers that Rajshri Deshpande played that character, but Rajshri is a female. She played the character named Subhadra, so we can clearly see that LLM is hallucinating. The first step in RAG would be to collect the information and build a knowledge-based documents. We will do embedding on these documents and store it in a vector store. To build the knowledge base, let us create a file called sacredgamescript.txt. I have copied some information from Wikipedia about Sacred Games. I have added some details about Ramakant Jadhav. To help us understand how similarity search in VectorDB fetches only relevant content, I have also copied details from the Wikipedia article for Squid Games. We can use the Langchain text loader function to load the document into memory. The embedding models work well with smaller chunked data, as it helps to retain relevant, meaningful information. Having the whole documents or very large chunks will make it include non-semantically relevant data. We will use the character text splitter and split the documents into chunks. We can see that there are 5 chunks for this example. We can then embed them using the Langchain openai embeddings. Langchain provides easy integrations with VectorDB. We will store the embedding into VectorDB using the feist.fromDocuments function. We are done with first major step, which is embedding the knowledge base. The second major step would be to embed the user query and do a similarity search in the VectorDB created above. Our query is, who is Ramakant Jadhav in Sacred Games, and which actor portrays Ramakant Jadhav in Sacred Games. To retrieve similar content from VectorDB corresponding to this user query, we will use the similarity search by vector function. The output of similarity search by vector returns a list of relevant information starting with most relevant to least relevant. The most relevant content is at index 0 and the least relevant is at the last index. In our example, we can see that the content at index 0 mentions some things about Ramakant Jadhav, but the content at index -1 mentions about Squid Game. Now we are done with second major step, which is retrieving similar relevant content from the knowledge base. The third major step is augmenting the query. Here we concatenate the query plus relevant document text to form the augmented query. The better augmentation technique would be have implicit message in the prompt asking the LLM to use the information from knowledge base. Here we concatenate the query and the implicit message also use below text as reference before answering, and then the relevant document text to form the augmented query. Now we are done with third major step, which is augmentation. In the last step, we feed our augmented prompt to the LLM, eagerly awaiting its responses. The LLM provides an answer, I couldn't find any information on a character named Ramakant Jadhav. It states that the show does not include a character named Ramakant Jadhav. Now, we can see how we have prevented the LLM from hallucinating. Instead, it acts like a creative and more knowledgeable maestro, producing the precise completion we desire. And there you have it. To summarize, we've journeyed through basic LLM prompting technique, then looked at hallucination. We then discussed a simple RAG architecture. We finally looked at sample code to bring all this into action. It's been an exploration filled with insights and algorithms. Thanks for watching. Stay tuned for more exciting adventures in the world of AI and machine learning. If you found this video helpful, don't forget to hit that like button, subscribe for more tech talks, and ring that notification bell to stay updated on our future explorations. Until next time, happy coding and keep the curiosity alive. Thanks for watching.